Welcome. Today we will be discussing uncertainty principle. This principle is one of the core principles in quantum mechanics. Now let us hear what it says. Now we are going to break it little by little. First of all, let's see what is position and momentum. And then we need to check what is uncertainty. And then what does simultaneously mean and what is arbitrary precision. So let's take them one by one. First of all, in classical mechanics, a particle moves in some direction. Okay. Now, in this direction it has some momentum, and this direction I will call as the x-axis. So this momentum becomes Ex. Now in this direction this particle will move with a definite momentum, and every time its position will be specified. However, in quantum mechanics it is not a particle that is moving, it is a wave. So in this sense, if a wave is moving, it cannot be localized into a single position. You know what I'm saying? So if a wave is moving, then we cannot say the whole wave is localized at a single position. It means a single wave just cannot have just a single value for x. So any particle which is behaving like a wave should not have a position, a specific position. So here we say that electron is a quantum particle and it will behave like a quantum particle does. So it is both like a particle and a wave also. So uncertainty principle makes sure that it is behaving like a wave, and in that sense it cannot have a single value, a precise, accurate 100% value for position. Same goes for the momentum. A wave moves with a momentum and so does a particle. But you cannot determine, or you must not be able to determine the exact momentum of the particle if it is behaving like a wave. Now there is a thing called uncertainty or the precision of these values. These values, how do we find position and momentum of a particle in quantum mechanics? We know it very well that we have got some operators, that these operators help us to find the values of these observables. The observables are momentum and position. So with the help of these operators we try to determine the values of the observables. The more solutions we get for this equation, the more values, the more eigenvalues we get for momentum and position. So if we plot a graph of any of these values, then the momentum value, for example, will be like this. So these are the values of momentum on y-axis and the probabilities of these momentum values on the x-axis. Let me denote it by phi x, and these are the momentum values. So there is a mathematical quantity that we define which is called standard deviation. That standard deviation is denoted as del p. This standard deviation denotes how spread the graph is. So if the graph is a flat one, then the standard deviation is more, and if the graph is like this, then the standard deviation is less. It means the momentum has a more precise value. So in a sense, the standard deviation shows the uncertainty in position and momentum. So this is for momentum and this is the standard deviation for position. I will write the formula, but I am telling you it is not important. In statistics, we write it as the summation of the individual values minus the mean value and the square of it divided by all the values possible. Similarly, we have an integral form of this del P, or I must say uncertainty and momentum. But anyway, these are not important. What is important is that we know what uncertainty is. It is not the inaccuracy in an instrument. We are not trying to measure the value of momentum of an electron with some instrument and saying that the uncertainty is arising due to the inaccuracy of that instrument. No, the uncertainty is quite an inherent property of a quantum particle. The momentum values are like this. The momentum values are not very precise, and so an uncertainty is attached to the particle like its mass, like its charge. So it is also a property that we define through uncertainty principle. The uncertainty principle is a more general principle. It does not apply only to momentum and position. It also applies to every other observable that is complementary to one another. It applies to all those pairs of observables that are complementary to one another. These are called the complementary observables. So here we go. Any two observables are said to be complementary if they do not commute. You must be asking yourself in the uncertainty principle that why we are discussing only momentum and position. Well, the uncertainty is linked in both of these. I mean to say, the accuracy of one or the standard deviation of one observable is linked to the standard deviation of the other observable. That is because these two are complementary observables. What I mean is, if on a wave function I operate with momentum operator and then I operate with the position operator, it will not be the same as if I had reversed the order. That is, if I had operated with momentum and then the position operator. These two values are not the same, and that is why we say that these two operators do not commute. This is the definition for complementary observables. Two observables whose operators do not commute are called complementary observables, and hence they will show uncertainty principle. Similarly, you have energy and momentum operators. So energy and momentum operators also do not commute. You can check that for yourself by putting the values of energy and momentum operators. We already know the momentum operator is h cross by I d by dx. Similarly, if you are trying to find the energy operator, then you must write h cross square minus, and on the bottom line you will write 2m and only x coordinate and only the Vx potential energy. Remember, the uncertainty principle applies to one direction only. So if we are taking the x direction of momentum, then we must also consider only the x direction of the energy. That means the energy associated with the x coordinate. So if you try and put the value of psi one by one and try to find this, you will find that these two values are not equal. In fact, we define a really important property called the commutator. Commutator is the difference between the effects of the two operators. It is defined as this. Now we will try to find the commutator of position and momentum. So first, solving the first half, we show it by So let us try to find the commutator for momentum and position. Here, putting the values, for x operator we multiply by x, and for p operator we multiply by h cross by I and differentiate with psi in the x direction. Similarly, we again multiply by h cross by I and differentiate with respect to x direction, and in the bracket we have x multiplied by psi. On the first term, we will just get the product of these variables and a differential of psi. However, in the second term, we will need to apply the product rule, as x and psi are both function of x. Applying the product rule, differentiating x for the first, leaving psi, and then differentiating psi, leaving x, we get a value like this. Now we will open the bracket, and so we will get three terms. As you see, the first term and the last term add to 0, and so our answer is just minus h cross by I and psi. Now I can multiply by I, and so I will get minus 1 at the bottom, and just like this. So my answer is actually I h cross psi. Now, so the commutator that we defined is just I h cross. We do not need psi because psi could be any function and is not dependable upon these two operators. So these two operators differ from each other in effect by IH cross, and this is the commutator. And why it is so important? Because the standard deviation of the position and the momentum is greater than equal to half of mode of the value or the average of the commutator, that is IH cross. The average is still IH cross, and the mode of this imaginary number is just H cross. And so finally the equation that we get is this. There we go. This is a general equation. So the general equation is this. So standard deviation in any two observables is equals to half of the mod of the commutator. So good luck and thanks for watching.